Hi everyone. In this video, we are going to talk about the second part of lesson 3.4. In the first part, remember we talked about special equations, or special linear equations, excuse me, horizontal and vertical lines. And today we're going to be talking about x and y intercepts of linear equations. The content that we're doing today with x and y intercepts in general works. It's just for linear equations, graphing the x and y intercepts has some extra special, it's just extra useful, which we'll get into. So to first start out this lesson, I just have a which one doesn't belong. And so you go ahead and pause the video and maybe pick a graph and write a reason why that graph doesn't belong in the set. I'm going to continue talking. So here's why I would choose graph B. Graph B is the only graph that is curved, so it is nonlinear. And we've talked about what makes something linear and nonlinear. Or maybe you chose graph C, and graph C is the only graph that's discrete, so it is not connected or continuous. It is discrete. So maybe that's why you chose graph C. Or maybe you chose graph D, which by the way is this line right here, not the x or y axis, because it's not a function. All of the other graphs are functions. They pass the vertical line test. Each input has exactly one output. So you notice I didn't start with graph A, and that's because graph A is the only one that is linear, continuous, and a function. So in a way, graph A is the one that has something in common with each one of these graphs, right? So that's maybe why you would choose graph A. So in graph A, and also in graph C, they are linear functions that have x and y intercepts. So let's get into our discussion of intercepts. An intercept, when I think of the word intercept, I think of intersect. And what am I intersecting? I'm intersecting the x or the y axis. So the x-intercept is when the graph intersects, the point where a graph crosses the x-axis or intersects it. So here's our x-axis down here, and this point right here, that is our x-intercept. And every point on the x-axis has a y-coordinate of 0. And so this point right here is -3, 0. And we're going to come back to that when we find intercepts. That's going to be important. The y-intercept is very similar, except for it's the point where the graph crosses the y-axis. Again, here is our y-axis. Our line crosses at this particular point right there. So that is our y-intercept. And this is the point 0, 1. So every graph, or every point, on the y-axis has an x-coordinate of 0. I keep misspeaking in this video, so I apologize. I'm going to really dig into that as I keep going. And one other key piece of information that we're going to see and notice in this particular lesson is standard form of an equation. So we've talked a little bit about slope-intercept form. That's our y equals mx plus b. That's how we defined a linear function. And there's a couple other types of iterations of linear equations. One of them is standard form. And so the equation for standard form is ax plus by equals c. And a, b, and c in this case get filled in with real numbers. They don't become variables. I'm using them as variables in this situation, but really only x and y are going to be variables. And so we might have a situation where it's like 3x plus 2y equals 10. That's an example of standard form. So the A, the B, and the C get filled in with actual numbers. When we get into chapter 4 and we learn to write equations, that's when standard form is probably going to make a lot more sense. But it's useful when there isn't a clear independent and dependent variable, which we've definitely been hitting hard. Again, we haven't had to decide who our independent and dependent variable is because the equation has been given to us. Sorry, so we haven't had to write the equation using that information, but we've had to pick it out from the equation. So let's take a look at a standard form of an equation and solving and finding intercepts. So equation 1 is 4x plus 2y is 16. And what we're going to do is we're going to find the x and y intercepts. And then I'm going to talk again about why that is going to help us graph the line, why the intercepts of a linear equation are particularly useful. So as we said on the first this definition, the intercepts are found or can be found because the other variable in the equation is 0. So at the x-intercept, the y is 0. And at the y-intercept, the x is 0. And we've been talking again, what is a graph? A graph of a line or graph of any equation is a visual representation of the ordered pairs that are solutions, okay? And that's why when we were graphing our lines before, we made a couple of input-output values in a table, and then we used that to graph the line. And so now we're going to do it by graphing intercepts. So first, let's find the intercepts. To find the x-intercept, I am going to set the y equal to 0. And again, this is going to give me the unique ordered pair that satisfies, that's the mathematical word, satisfies this equation when y is 0, and then we're going to get the particular x that's paired with that y at 0. Now anything times 0 is 0, so we don't need that part. And that simplifies our equation to 4x is 16, and we do our beautiful inverse, and we get x is 4. So the x-intercept is 4, and if we wanted to write this as an ordered pair, it would be 4, 0. For the y-intercept, I do the same idea, except for this time, the x is going to be 0. Again, 4 times 0 is 0, so we're left with 2y is 16. And we get y is 8. So the y-intercept is 8. As an ordered pair, that would be 0, 8. But here's the cool thing. These intercepts actually help us graph the line because 2 points determine a line. And so we have 2 points, and we can actually graph this line just from those intercepts. Whereas if we have a different type of equation, like something that is curved, okay, this won't give us enough information to graph this particular curve if we just knew the x and y intercepts. It might tell us something about it, and certainly those are information that is useful and helpful and tells us things, but it's not enough to graph. And with a line, the intercepts are enough to graph. The only exception to that, because I feel like there's always an exception, is when the graph passes through the origin. Good news, we're not going to have any of those. So I'm going to do equation 2. If you would like to challenge yourself and pause the video and try yours on your own, and then go ahead and check your answer and restart the video, great. If not, work through this example with me. So the x-intercept, again, we're letting the y be 0. So I'm actually just going to go ahead and write 2x is 4. I'm going to kind of remember that when y is 0, that value in that part of the equation becomes 0, and I'm left with 2x is 4 and x is 2. This graph is going by 2, so I'm just careful about that. For the y-intercept, one thing that I am very aware of is that there is a negative in front of this y. So when my x is 0, I get negative y equals 4. And that's the same thing as negative 1y equals 4. If that's something that you kind of need to unpack a little bit, or really need to remind yourself of, you can always go ahead and substitute 0 in for x, remember that's 0, and then do the simplifying from there. That might be something that you need to do. When we divide by -1, we get y is -4. And there. And again, we can then graph the line. So for our last part of our notes here today, we're going to take a look at a word problem. Again, we're not writing our own word problem, but I want to drive home the idea that we necessarily can't identify an independent and dependent variable here. So you're bringing chips and pretzels in for snack. Maybe it's advisory snack. Bags of chips cost $4 each, and bags of pretzels cost $2 each. And we have a budget of $20, and we want to spend all 20 bucks. So the equation 4x plus 2y equals 20 models this situation. So what do x and y represent? Well, let's look at the x. We're doing 4 times x, and what do we know about 4? It's the cost of 1 bag of chips. So x is the number of bags of chips. And we're going to put that on our x-axis, and we're going to label it. I'm not going to do the intervals on my axis yet, because I want to wait and see what my information is. So for y, it's the 2 has to do with the pretzels, and so y is the number of bags of pretzels. My screen does not like when I write sideways. This might be a little crooked. Again, we'll deal with our interval in a second. So we're going to start finding the intercepts. The x-intercept gives us 4x is 20, and x is 5. And the y-intercept gives us 2y is 20, so y is 10. So I know on my x-axis I have to go up to at least 5, and on my y-axis I have to go to 10. The wider, or the smaller the intervals, the more accurate graph I'm going to get. So for example, I'm not going to go by 5s. I'm not going to put 5 here and 5 and 10 here, because then my graph looks like that. And that's really tiny, and it's not giving me a lot of information. So for my x-axis, I could go by 1s or even halves, but I'll go by 1s. So I'll go 1, 2, 3, 4, 5, and then I'll go by 1s on my y as well. Here's my y-intercept. And again, what's happening there is I am buying no bags of chips and 10 bags of pretzels. And for my x-intercept, I am buying no bags of 5 bags of chips and no bags of pretzels. Now again, yours should look a lot better because you should use a straight edge here. I'm going to try my very best. All of these represent possible solutions to the equation, but technically in this problem situation, is our domain discrete or continuous? If you said discrete, great job, because this can only be existing in whole bags, right? So our domain is discrete. We are going to represent it as a continuous line, but just reminding ourselves as we're thinking about the possible answers, in this case, it's whole numbers. So to find another solution, I'm going to try my best to find a nice integer connection point, right? I don't want to pick something in the middle because that's not going to give me information that's going to be actually useful. So I think the number 3, 4 will work. So let's just see. And I'm going by the graph. So I have 3 bags of chips, so $4 times 3 bags, plus $2 times 4 bags of pretzels. Is that 20? Well, 12 plus 8, is that 20? And yes, it is. That works. So 3 bags of chips and 4 bags of pretzels. And we are running out of time in our video, so I do want to wrap it up here. But there are other answers to this on this line, and we can talk more about that in class. Great job, everybody.